Is this thing on? Nej, det er den andre typen. Den som...
Den der, ja.
Ja. Jeg har en som springer og henter den, så det går bra. Tror jeg. Okay, well, we'll see how this works. I have a runner for a cable. My impromptu power supply didn't work. I don't have enough USB ports, so I thought, okay, well, let's use this battery to power the microcontroller. That's plan failed. So today, the plan is to talk. Well, the plan is number one, stay awake for me. That's going to be a bit of a challenge. The plan is to talk about why we write multi-threaded programs and the challenges that arise when we have finally found out that the conclusion for writing multi-threaded programs is that it is in fact useful. And then cover some of the material that you will need for the exercise 1 and exercise 2. Here comes my cable, possibly. Yes, it is in fact the correct type. Also, I need to start recording. This seems safe. Okay. We have power now. And we have our first blinking LED. So, yay, mission accomplished. This is the standard hello world type program for microcontrollers. Who here has already kind of written this type of stuff? So anyone here who has not programmed a microcontroller at all? Okay, so everybody is at least somewhat familiar with this, the goings on over here. So this is, this code is not particularly interesting or challenging to write. You turn on the LED, you wait some time, you turn off the LED, and then you wait some time. Easy. Okay, let's do this, but we want to do it with 2 LEDs. Any suggestions? I want to blink 2 LEDs, and I want one to blink 2 times, or once every second, and I want one to blink once every 1.5 seconds. Or no, once every 0.75 seconds. No, different periods. I want 2 LEDs to blink with different periods. Suggestions? Timer interrupts? Okay, yes, that is a valid solution. Let's say I want to blink 2 LEDs, but I'm running on Windows, and I don't really have the access to timer interrupts.
I mean, you have some delays there. You could probably do something clever. And
yeah, exactly. So let's do something clever with our delays. So I'm going to do the, you know, the baking shows where they're like, oh yeah, this is one I prepared earlier. Well, yeah. So, yeah, this is one I prepared earlier. Does Control Tab work? Yes, it does. Okay, good. So yeah, I prepared this one earlier. Hopefully, no, that keyboard shortcut doesn't work. So do we have? Yeah, we have two LEDs now, and they are in fact blinking with different periods. So mission accomplished, I guess. Now I want you to take a look at the code here on your left. and I want you to think about code quality concerns here now. Because ultimately this is what it boils down to. Let's look at the code quality concerns. Number one, objectively, does it work? Yes. Does it perform well? Like, is it power efficient and high performance? Well, it's blinking LED, so whatever. We can't really say anything about that. So under the objective code quality criterias, this is perfect. This is the best solution ever. Like, it can't possibly get any better than this. But of course, there's something missing here. What's missing?
If you want to try to look at that code and figure out what's actually going on, that's not particularly easy.
Yes, so figuring out what's going on by reading the code isn't easy.
In addition, if you want to change any of the blinking frequencies, it's a bit of a hassle.
If I want to change periods, it's a bit of a hassle. Any more? Any more takers? Well, this guy really enjoys taking.
If something was wrong, you'd have a hard time fixing it.
If something was wrong, I'd have a hard time fixing it. Yes. So the first one is hard to read. The second one is hard to change, and the third one is hard to fix bugs. And the latter two are kind of in the same category of hard to maintain. So the question that I'm not going to answer today, but I want to answer at some point in the future is, what does it mean for something to be hard to read? And what does it mean for something to be hard to maintain? Right now, I'm just going to say that these are things that you need to pay attention to. So keep that in mind. Try to wrestle with the idea itself, and try to, when I go through more examples, try to think along those terms a bit more abstract than you're perhaps used to. I just want to see what happens when I expose that idea to you. Okay, so suggestions for improvement. Because we want to make it more readable, and we want to have different periods. If I'm going to do 19 versus 20, this expands massively. So I want to have one that runs 19 times a second and one that runs 20 times a second. The interleaves are really bad.
Square root of 2.
He wants the square root of 2 as a period. Okay. Well, I don't see a problem with that as long as your clock crystal is also divisible by the square root of 2. Well, any suggestions before I suggest? I see a finger.
Find some common frequency and make counters.
Find a common frequency and make a counter. Yes, you are absolutely on the correct track. What is the common frequency of all frequencies? Again.
As fast as you can.
As fast as you can. That is actually the correct answer. We can't do anything at a faster rate than the clock in the CPU itself. So, well, arguably the fastest frequency you can go is the clock frequency. But of course, if we use all our clock power counting the counter, then we don't have any clock frequency left over to do any work. So as fast as possible doesn't mean actually as fast as possible. It means as fast as possible so that we have time left over to do actual useful work. So let's just say, for now, let's just do 1 millisecond and say that that's fine. So let's do a clock counter that counts every 1 millisecond. So this is one I prepared earlier. Control tab. Oh, we need to get the font size down a little bit. Clicky the thinger. I'm almost surprised that the code works as well now at this point. Okay, so let's check the blinkers. Yep, they're blinking. So it's still within spec. Now let's have a looks and peepers at the code. There's some arguments to be made about, well, the LED states and you do divisible by a constant value or something. If you want to, well, we have one time where we're turning the LED on and we have one time where we're turning the LED off, which means that we either need to have one counter for on times and one counter for off times, or we need to do on and off on the same counter and then figure out what the state was. So either we need to save the state with these LED states, or we need to have two different counters for both, and I figured that preserving the state in a variable was the correct solution there. Is it the correct solution? Question for the audience, was that the correct solution, or should I have had one counter for each? So I had divisible by 200 equals 0, and then divisible by 200 equals 100.
I mean, that's another comparison for each.
Yeah, well, one comparison for ons and one comparison for offs, or one comparison for both, and then preserving the state in a variable.
Yeah, that's my point. There's one more comparison. That's not ideal.
Yeah, so one more comparison is not ideal, and then the question for the audience, generally speaking, is what does not ideal mean? The point I'm making about these kind of code quality things is you already know what the correct answer is. It's an unknown known, I guess. You know what the answer is, but you don't quite yet have the vocabulary to articulate it. You don't quite have the framework to expose the correct answer in more situations than the ones you have already encountered. Like if you're going to make something new, you don't necessarily know what the correct approach for code quality is yet because you haven't wrestled with this idea enough. So, this looks fine for the most part, but there's still a couple of issues going on here.
I'm just wondering, you don't reset the counter any time. Should you do that?
I don't reset the counter. 32-bit counter, 1 millisecond. That's 4 million milliseconds. That's it's a while, but yes, of course, that's a valid concern. I can't really argue with that. At some point, this might not add up perfectly. That's true. I mean, that's true for every computer, but at this point with 64-bit computers, well, there was this whole Y2K thing, if you guys remember that, where, oh, once we reach the year 2000, everything's going to wrap around. And then there was another one, which is 2031, I believe? Or when is it the 32-bit values? Right now, it's the default counters in most systems are 1 second, the number of seconds since January the 1st in 1970. And if you do that in 32-bit counters, it's sometime, I think it's 2031 or something like this, where it's going to wrap around. And the answer to that concern is that, well, if you're not running 64-bit systems by 2031, that's your fault. So, but yes, of course, it's a valid concern, and if this was going to be running for that many years, I would try to figure out how to do a 64-bit counter or do something else, but yes. But it's not exactly the thing I'm looking for. I'm looking for two other things. I think I'm looking for two other things, at least one other thing. Let's say we were doing something more substantial than LEDs, something that required some amount of calculation. Perhaps something that required a lot of calculation. I want to go for someone different for once. Yes?
It's not constant time?
It's not constant time. Yes, we are using a delay. We're not delaying until. That would help, but it's not the whole story. I don't know if you want to continue with the whole story or... No? Okay, someone else can dig the whole story. You can attempt the whole story.
You're assuming that only the delay is what takes time here. That was maybe the point.
Yes, well, yes, I'm assuming that only the delay takes time, but more than that, I'm also assuming if we did do a delay until 1 millisecond since last time, however we would do that, I'm not quite sure how we would do that, but let's assume that we can. Even if I did do that, what if something in that while loop took more than 1 millisecond? Then we can't delay until 1 millisecond past the last time because that's in the past. We can't delay until the past. We can only delay until the future. So what's the problem with that? I risk skipping the counter so it doesn't actually trigger. Yes? But I want something a bit more fundamental than this. Because we can fix the skips with doing like greater thans and less thans and something like that. What are these two things? These two things are sharing something. I want to blink two LEDs in such a way that they are not sharing anything at all, because they're completely independent tasks. But the thing I want them to share is the same processor. But in this case, they're sharing more than just the processor. They're sharing some kind of metaphysical code space. That's one concern. They're not visually separate when they could be. And the other concern, which goes back to the ones with timing, is that if one of these things happens to not cooperate and be stuck in an infinite while loop, for example, or at least a very long while loop, then the other things cannot run. So this is a cooperative system. If something does not cooperate, it breaks. So the latter of these two, the cooperative one, is pretty much that needs to be fixed. And the first one, it's sharing code space. That doesn't need to be fixed from like a technical perspective, but it should be fixed from a code quality concern perspective. So, what's the solution? I want to make sure that these blinkers, or more advanced non-blinkers, things that can execute and also not yield, they don't cooperate. I want to make sure that I can stop things that are not cooperating from running so that I can run something else. How do we do this? All the real-time systems people already know, so they're just not answering, and that's fine. This guy is just on the ball.
It's what we're here for, right? So it's threads.
It's threads. That's why you're here. Well, yeah. Well, not just threads, but in order to use threads, to misquote Carl Sagan, in order to use threads, you must first invent the operating system. So, here's one I prepared earlier. Oh, hey, would you look at that? Just import operating system. Well, isn't that useful? What a joke. Oh, did I just not? Yeah, I didn't mark it, and I did copy. Of course, we can't do quite that. And then there's always the hopefully this compiles part. Build succeeded. Output succeeded. Okay. So we're going to have to look at the code in two sections. First, okay, we can fit everything into one page. There's one thread for blinking LED 0, and then there's one thread for blinking LED 3. Let's see. Do we have any blinkers? Oh no, I didn't enable the absolute professional, by the way. Not quite. We have a slight issue going on here. Can anyone spot the slight issue? This guy's going to get an A in the course. Yeah.
Is it the delay is it delaying on the CPU directly. So it's delaying for both threads at the same time.
Yes, is it the delay? Is it delaying for both threads at the same time? And the answer is yes. In fact, it's not only delaying for both threads at the same time, it's delaying for all three, because main also has a bit of a while loop going on there. So first, let's just explain what this little thing does. First thing is these calls to spawn. And spawn means create offspring, create your children threads. These things are now running concurrently on the CPU. Let's do a little bit of word definition time. What's the word? Concurrent. What does concurrent mean? Anyone want to throw themselves out, pretend to be a dictionary? Yes.
At the same time.
Concurrent means at the same time. Okay. Let's do another, what's the word? Parallelism. Let's do the difference between concurrency and parallelism. Any takers? Because these two are different, and I think it's important that you understand the difference, because, spoilers, it might show up on the exam. Okay, so concurrent, or if something is running in parallel, it is actually running at the same time. And in order to do this, you will need more than one CPU core. If something is running concurrently, it is not necessarily running exactly at the same time, but it's running in such a way that it is perceived to be at the same time because you're interleaving them faster than the dynamics of the program itself. So in this case, I am interleaving these threads every millisecond, but they're running on the same CPU core. So they're not running at exactly the same time. They're just running interleaved, so they appear to be running at the same time. But of course, the thing that is messing with this program is the delay ms. So we're going to have to use something other than count CPU cycles here. We're going to have to use a proper sleeping function. So it's always fun using a demo that you haven't used in a year and you're wondering, does it still work? Well, the periods are a bit different now. I'm using 100 milliseconds on one of them and 300 milliseconds on the other, so, or 500, so. Not quite exactly the same example, but 1, 2, 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 2. Okay. So this is correct. So now it's working. We remove the CPU counter, cycle counter delays with sleeps. And the sleeps, well, we can go into how the sleeps work, but we're not going to go into exactly how the operating system works right now. So, what have we achieved? What have we achieved with our threads? That's the question. Let's look at this part. This is the interesting part. And just for fun, let's see where we came from. What have we done? Let's do a before and after comparison. Who likes before in green text? Who likes after in normal text? Who does not like after? Does anyone have any objections? It's like, no, this is the wrong move. Okay, I'm going to say interesting, but I'm not going to say that because it's not very interesting because you already know this. Who here has actually programmed multi-threaded before? A few of you. Who here has not programmed multi-threaded before? The vast majority of you. So then the question is, why does it fall so naturally to you to prefer the multi-threaded version? Like, actual legit question, why do you prefer it? How did this happen? It's intuitive. Okay, where does intuition come from? Are we just like born with it, or is it just evolution? Like, what happened there? Okay, the Mr. A candidate again.
It's scalable. It's easy to scale.
It's scalable. It's, yes, you can just add more threads and it doesn't interfere with everything else. Yes. Why do you prefer scalable?
Because I might have to scale it.
You might have to scale it. You like adding things. Or you are aware that the world is more complex and that there may be things that you haven't foreseen, which means that there are things that may change and things that you may need to add. So you are aware of the future. Well, that's a good thing for humans to be. Any more? Yes?
You can add other things to main that is not the blinking LEDs now.
Oh, I can add more things to main as well. I can use main as a separate thread. Yeah, of course.
It's a higher level of abstraction, so you can see, like, if you're just interested in blinking, and we can, okay, this one blinks one of the LEDs, this one blinks the other, but you can go into the functions if you need to, but you don't have to.
It's a higher level of abstraction in the sense that, well, let's see if I can formulate your argument precisely so that everyone hears it. A higher level of abstraction in the sense that you don't need to go into each individual function to be aware of how the program works. You can just look at, this is one LED blinker, now this is another LED blinker, as opposed to the commented out one there, which is, this might be a couple of LED blinkers. Yeah. So there's a precision in language in the sense that there's a precision in the way that you use the programming language here. Okay. Yes?
It looks a little more pretty.
It looks more pretty. Yeah, well, this is, I know people like not talking nicely about prettiness concerns with code, but it is, I mean, we're humans, we like pretty stuff, we like shiny stuff. So if your code looks shiny, that's not a negative thing, that's actually a positive thing. You're going to be looking at your code a lot, so if it looks nice, that's just nice. And also, if it does look nice, there's probably something about it that is a positive trait that is more than just looking nice. Because we like nice things for a reason. Did I have more stuff here? Oh yeah, we do have more stuff. Okay. Let's get into some more complex stuff.
What about we're used to think on parallel things because the world around us is full of parallel things happening at the same time?
I'll repeat it for the microphone's sake. What if we like the parallel version because the world around us is full of parallel things? So, well, I guess the assumption is that parallel things fall naturally to us. Yes. That is actually the major point. So there's this, there's lots of programmer humor out there on the web. And one of them is, well, you have a problem, so you decide to use threads. Now you have two problems. And this is where I'm running out of USB ports, so we'll see how this works. Hopefully Atmel Studio 5 or 7 is stable enough to handle this. Yes, Termite, I do want to open you. Yes, Termite, I do want to connect you. No, Termite, I don't want that. In fact, I do actually want that. No, I don't. I want the other one. There we go. Everything is fine for now. Let's see if something bad happens. What bad stuff could happen here? Oh, there we go. It happened. Unfortunately, Termite doesn't let me increase the font size, so I'll just read it out loud, I guess. You have a problem, so you decide to use threads. Now you have to, so you decide to use threads. It's the best I could do. So, what happens?
Looks like the two threads tried writing through the UART at the same time.
Looks like the two threads tried writing through the UART at the same time. Well, yes, it does look like they tried using the serial port at the same time. They were writing to the screen at the same time. Yes, correct observation. I am stupid and I don't see the problem. What's the problem?
You cannot lock down a resource to a single thread.
We- You
When a
skipped
thread
over the
is-
problem and went straight for the solution.
Yeah.
Well, okay, so the solution was we can't lock down a resource so that it's only usable by one thread at a time. The problem was that we had something that was used by two threads at the same time. And the problem really was that the text is mangled. That's the problem. And the solution to the problem is unmangle the text by not letting things run at the same time. So, okay, these were the problems we encountered, or I said we were going to encounter yesterday, which was problem number the first, how to run things at the same time. Okay, solved. Use an operating system and threads. And then problem number the second, how to make things not run at the same time. So, now we need to stop things from running at the same time. Geez, well. Okay, but the word you used, resource. Let's implement resources. So, wait, hold on. Yeah, this is one I made earlier. Oh, look, a resource. Oh. Where did you find the spoilers, by the way? It's like, it's interesting that you're using exactly the same word. I mean, I say interesting, I mean, it's obviously the correct word, so. That's why it's, of course, not the standard word in any operating system. I mean, why would it be? Build succeeded, yes, but we can't. Of course you can't. I know, because I only have 2 USB ports. Wait, hold on. Okay, and now we encounter a problem. Well, I say we encounter a problem. We've solved one problem. Well, we encounter well, okay, let's first look at how this works. Before we use the UART, before we write to the serial port, we acquire some kind of resource which represents the UART. So we take the resource and say, now we have sole ownership over the UART port. And what happens here at some deep operating system level is that when one thread calls OS resource acquire, it holds the resource such that if another thread tries to call resource acquire, it will block. It will not continue executing. It will stay there until the first thread calls OS resource release and then give it to the other one. In this way, we have enforced that only one thread can use or can run any code that is between a resource acquire and a resource release for that resource. You can of course have different resources, so that one thread acquires one resource and then another thread acquires a different resource, and they can run simultaneously. But for the same resource, they cannot run simultaneously. So this, well, it appears to be working. Has it ever not worked, by the way? I haven't been looking.
There was a small glitch.
There was a small glitch?
It was not interleaving though.
One missing letter or something.
Oh, well, let's just blame that on UART. And I mean, have you seen my UART cable? It's just like a brown wire. So if this isn't perfectly connected, you know, it's just that might just be the reason. But yes, the problem we are encountering now, which is might not be a real problem, but it is also simultaneously a very real problem, is that we can't really verify that this works anymore. Because there might be a bug, it just doesn't show up very often. In fact, it might never show up, but still be there. And that's, you will encounter this kind of thing when you're working on the Elevator project, where there are bugs that you don't know exist, and then suddenly they show up and you go, oh shit, there's a bug we need to fix, and it never happens again. And also, things that are timing related, there's a bug, and then you add printfs because you're wondering what the state of the program is, and then the bug disappears. Because the printfs influence the timing such that it never appears again. That's also very common. And then the solution is, of course, just leave the printf in. So, okay, well, I've reached the end of live demo examples. What is time? Time is 55. Okay, well, that seems like a reasonable time to take a break, but let's see. Is there anything I should say before I take a break? Yes, the project specification stuff. If we have time at the end, I want to see if we can figure out which one is in fact better. So if you haven't looked at both variants, I'll link the second variant on Blackboard. It's in project-2017. If you do want to spend 2.5 seconds or minutes looking at just vaguely comparing the two on in the break, that would be nice. It's not mandatory, but I want to see if there is in fact a correct solution for which one is the best one. Because it's a maintenance burden to manage both of them if there are in fact things that need to be changed. That's one thing. And then the other thing is, no, there is no other thing. That's it. See you in like 17 minutes, I guess.
Uten at mikken er i nærheten.